Good morning, ladies and gentlemen. I hope today finds you well. Today we're going to talk a little bit further about specifically refraction and the wave behaviors that we've been discussing so far. I want to do a very quick review just to remind you of a few important points that are going to come up today. First thing from a little while back, as we were talking about sines and cosines, remember sine on a right triangle is the opposite divided by hypotenuse. It's the ratio of how long the opposite side is compared to the hypotenuse. And something we do want to point out is just how the angle affects the sine. And so here at a smaller angle as compared to the triangle over here, what we have here is you have a smaller side divided by the hypotenuse. But as the angle gets bigger, you'll notice the opposite side gets larger. So essentially what we have is that at a small angle, you will have a smaller sine of theta when you calculate your number, a smaller ratio of the opposite compared to the hypotenuse. But at a larger angle, you have a larger side being divided by the hypotenuse and you end up with a larger number. So again, at a smaller angle, you end up with a smaller answer for the sine of theta. But at a larger angle, whenever theta is bigger, you end up with a larger answer when you get the sine of theta. So the sine of theta scales with the actual angle. Something else we wanted to review very quickly, when we talk about refraction, remember that's the change in velocity and wavelength that occurs when a wave changes between media. So as you go from a fast medium to slow medium, the velocity and the wavelength can change. Now remember, velocity, that's both speed and direction. And sometimes the direction will change, but if it hits perpendicular to the boundary, that's the only time the direction would not change. The speed will always change when it undergoes refraction. It's basically the change in speed that causes the change in wavelength and usually a change in direction when the wave refracts. So a couple quick reminders about the ways that this works is that if you've got your boundary right here, remember that this dotted line represents the normal line, and the normal line is 90 degrees to the boundary, the barrier between the waves. The wave enters from one medium into another. If the wave comes in this direction, remember that you measure that angle from the normal line. That's why we're drawing that. That normal line is 90 degrees. So whatever angle this may be, we can call that the angle of refraction. And as it goes into a slow medium, what will happen is that the angle will get smaller. So instead of going straight, the angle between the wave and the normal line will become smaller. So even though I don't know an exact number, I know that it's going to bend towards the normal line to make a smaller, I mislabeled that. This is the angle of incidence and this is the angle of refraction. The other thing that also changes, recall, is the wavelength, the distance between the waves. So if these are water waves coming in and you see the crests coming in and they're spaced about this far apart, you've got between in here and there, that's your wavelength. As it slows down, as the speed becomes smaller, the angle becomes smaller, and the wavelengths become smaller, so they are closer together. And then the complete opposite happens. If you recall, if you go from a slow medium to a fast medium, as the wave comes in that direction, as the waves are moving towards the boundary, you've got your angle of incidence, but because it's faster, it's going to speed up. So instead of bending towards the normal line, they're going to bend away from the normal line to make the angle bigger. So that would be something that looks like that, where the angle of refraction is now bigger. And if everything's getting larger, that means the distance between the waves will also get larger. So your waves would be spread even further apart. You'd have a larger wavelength. So that is a quick review of about what we've already been through. Next, just a little bit about how waves behave, different types of waves and different materials. These will be coming up. So far we've talked a lot about water waves. But we will be getting to sound waves and hopefully light waves before we end the school year. So in water waves, deep water versus shallow water, this we've already discussed. Recall that, let's move this up so you can see more easily. In deep water, that's where the waves move faster. So in the deep ocean, the water waves can move very fast, but when they come towards shore and the water gets more shallow, as the beach comes up towards the surface of the water, then that's where the waves slow down. Sound waves. As far as air, if you change the temperature of air, that has a noticeable effect on the speed of sound. So in cold air, the waves travel more slowly, but as the air heats up, the molecules vibrate faster. That gets them to bump into each other more quickly as a sound wave comes through. And so those, in hot air, the waves travel faster. And then finally, when we get to light, in general, what happens is if the material is low density, then that's when the waves travel fast. And if the material is high density, that's when they travel slow. So low density substances would be, for example, air. And higher density substance, where it travels more slowly, that would be substances such as water or glass. And because it slows down so much when it gets into those substances, that's why you see a bending of the waves as it refracts. Next, just a little bit about how waves behave, different types of waves in different materials. These will be coming up. So far we've talked a lot about water waves, but we will be getting to sound waves and hopefully light waves before we end the school year. So in water waves, deep water versus shallow water, this we've already discussed. Recall that, let's move this up so you can see more easily. In deep water, that's where the waves move faster. So in the deep ocean, the water waves can move very fast, but when they come towards shore and the water gets more shallow, as the beach comes up towards the surface of the water, then that's where the waves slow down. Sound waves. As far as air, if you change the temperature of air, that has a noticeable effect on the speed of sound. So in cold air, the waves travel more slowly, but as the air heats up, the molecules vibrate faster. That gets them to bump into each other more quickly as a sound wave comes through. And so those, in hot air, the waves travel faster. And then finally, when we get to light, in general, what happens is if the material is low density, then that's when the waves travel fast. And if the material is high density, that's when they travel slow. So low density substances would be, for example, air. And higher density substance, where it travels more slowly, that would be substances such as water or glass. And because it slows down so much when it gets into those substances, that's why you see a bending of the waves as it refracts. Now for the new material today, we're going to introduce you to a formula for refraction, and basically what it discusses is the ratio of how the speeds compare to each other and how that relates to how the angles compare to each other and how that also relates to how the wavelengths compare to each other. So it's actually not that bad. What we say is if you have the speed in substance 1 and you compare that to the speed in substance 2 as it goes from one medium into the other, that ratio of those two speeds will also be the exact same ratio as the wavelengths. So in other words, if the speed in substance 1 is half the speed as it is in substance 2, then the wavelength in substance 1 will also be half the wavelength as it would be in substance 2. And there's one more relationship we have here, and that relationship is, how does that relate to the angle? Now we're not going to measure the angles directly. It's not going to be angle 1 and angle 2. This is why we discussed the sine earlier. If you calculate the sine of angle 1, then it'll have the exact same ratio to the sine of angle 2 as the wavelengths and the velocities did to their counterparts. So this is the general formula. We can set any of these ratios equal to each other. So you can take the speed ratio and set it equal to the sine of the angle ratio. Any of these can be set equal to any of the others. Now, to make things a little bit more easily when we rearrange these, because everything's equal to each other as you go across the ratios, we could flip that upside down. So depending if you're looking for the velocity in the first substance or the velocity in the second substance, if you're trying to find the velocity in the second substance, we could rearrange this. It would take a little bit more work to leave it as is, but what I think will help you a little bit more easily rearrange that is you could just go ahead and invert everything. So the speed of substance 2 over the speed of substance 1 will be the same ratio as the wavelengths to each other. Correct that. And that will also be equal to the ratios of the sine of the angles. We'll do some example problems with these, but essentially what we're saying is you can either write it this way or this way. If you're looking for substance 1, you probably want to have the version with substance 1 on top. If you're looking for the velocity, the wavelength, or this angle of substance 2, then you probably just want to write it this way. This will save you a few steps in rearranging and probably help you make a few less mistakes. So here we got our example problems. Earlier today I did a little bit of research about wave speeds for earthquakes, just to try to come up with a problem that was pretty accurate to something you might actually come into contact with. So we've got an earthquake. They cause seismic waves to travel through the earth. In this example, as you measure how quickly the earthquake waves, the seismic waves, travel through granite rock, they travel through granite rock at about 5,000 meters per second. So we'll go ahead and call that, since we know that's a speed of velocity, we'll call that velocity 1. As the wave travels through water, so as it's, for example, going from a mountain, and then the mountain ends and the ocean or a lake begins, the wave will change media as it goes from the granite to the water, and in water the speed's going to be different. So this is the speed in substance 2. And if you were to actually photograph the water as the earthquake waves are coming by, you come up with a wavelength between the crests of about 580 meters. Now this is the wavelength in the water. We've kind of declared water as substance 2, so this would be the wavelength in the second substance. And we want to know what is the wavelength of the earthquake waves in granite. That was the first substance we were talking about, so what we were looking for is the wavelength in substance 1. So if we go ahead and set up this relationship, you've got your original formula, which if we take a look at that again, we'll bring that back up here. We had these two formulas. Since we are looking for the wavelength in the first substance, we're going to use the version that has the ones on top. And what we have is we have velocities and wavelengths, so we're going to use these two relationships. So speed 1 over speed 2 is the same ratio as wavelength 1 over wavelength 2. So if you're trying to find wavelength 1, we just need to get rid of the other stuff. How do you get rid of something that's on bottom? You multiply it to move to the other side. So that's going to go over here, and what you end up with is that the wavelength of the waves in the first substance, in the granite, is going to be equal to the speed in the granite times the wavelength in the water, and you're going to divide that by the speed in substance 2, which is the speed in the water. So we've just rearranged that to go ahead and use this formula, and then it's just a matter of plugging in your numbers. Now actually what I'd like you to do is go ahead and pause the video for a second, plug in your numbers, see what you come up with, and then let's check your answers. I'm going to go ahead and assume that you've taken the time to work that out. If we plug in our numbers, what we have here is 5,000 meters per second, and you multiply that times the wavelength of 580 meters, and you divide that by 1,450 meters per second, the speed of the earthquake waves in the water. And if we go ahead and multiply those out, we've got 5,000 times 580 divided by 1,450, and that gives us right at 2,000. So our number is going to be 2,000, but as far as the units go, what you see here is we have meters per second divided by meters per second, so those cancel out, and what you have left is meters. And that makes sense because we are looking for a wavelength, and wavelengths are measured in meters. So that would be your answer. And again, we're going to point out what happened. The speed, what did it do? It went from 5,000 down to 1,450 meters per second. So it slowed down, and what we said is that the wavelength, the angle, and the velocity will all change in the same way. So if the speed slows down, then that means we would also expect the wavelength to decrease. So you started out with a wavelength of 2,000, but as the speed decreased, you see the wavelength decreased from 2,000 to 580 meters as well. And then for our second example here, this is one that involves angles. In this example, we've got a water wave in the deep ocean, and it is moving at 120 meters per second. So that would be the speed of our object at the beginning. We can call that speed 1. And it slows down to 20 meters per second as it reaches shallow water. Remember, as water travels from deep to shallow water, it does tend to slow down. So right there, we're going to call that speed 2. If the waves are traveling at an angle of 45 degrees in the deep water, at what angle do they move in the shallow water? So this is our angle in the first substance, the deep water, and we want to know the angle in the shallow water. That would be angle 2. Now, whenever you've got the angles, I honestly believe it helps to go ahead and make a drawing, and that doesn't have to be overly complicated. We're just going to sketch it real quick. So if we have our boundary between the deep water and the shallow, which is equivalent of saying in deep water we know it moves fast, in the shallow water we know it moves more slowly. We're going to go ahead and draw a normal line, which is 90 degrees to the boundary. So we're going to approximate that. And it was going 120 meters per second at an angle of 45 degrees, so it approaches here at about a 45 degree angle. Now please remember, this is where every year, and I feel kind of bad because I know we're out of school right now, so it's a little bit hard to get the practice. But when you measure the angle, please remember, this is your boundary. Between the deep water and the shallow water, and then this is your normal line right here. And when you draw these angles, if you draw the direction the waves are moving, they're basically their velocity vector. It's always between the direction they're moving and the normal line. It is not between the direction they're moving and the boundary, and that is a common mistake. So the angle we're talking about is this angle. That angle is 45 degrees. And it says we're looking for the angle to come out at, and so after it passes through, we know it's going to move in some direction, and we need to know the angle. Now, since we do know that it's moving in shallow water, which is slower, then we'd expect that line to bend towards, for that angle to get smaller, since the speed is also getting smaller, so it's going to create a smaller angle by bending towards the normal line. So I'm going to say I expect it to look something like this, and that is the angle 2, the refracted angle that we're looking for. Let's go ahead and think about, if we're looking for angle 2, if we look at those formulas we had again, we said it's the same formula, it's just inverted, but if we're looking for the second substance, go ahead and have it with the version that has the second substances on top, just to make rearranging the formulas more easy for you. And so we've got angles and we have speeds. So we're going to compare this ratio to this ratio, and we'll go ahead and write that down. The speed in substance 2 divided by the speed in substance 1, that ratio will be the exact same as the sine of the second angle divided by the sine of the first angle. So we're looking for angle 2. We want to get angle 2 by itself. The first thing we can do is move its denominator. When we multiply it to move to the other side, that moves it up here. So we can say the sine of angle 2 is equal to this times this whole fraction. So that would be V2 over V1 times the sine of angle 1. And this is where, if your trigonometry is a little bit lacking right now, just due to maybe not having a lot of experience so far, I want to remind you, we're looking for the angle, not the sine of the angle. And so how do we get the angle by itself? You use the inverse sine when you move it over here. So just remember this part. To get the angle by itself, you simply say this is the inverse sine of the whole statement that we had before, V2 over V1 times the sine of angle 1. And I know everybody has different calculators, but on this calculator, to get the inverse sine, you just simply have to do the second function above sine. So if I clear that off and I hit second sine, you'll see sine with a little -1, and you can enter in parentheses all the numbers that may go into that. Now that we've got it set up, it just becomes a matter of plugging in the numbers. And so as we go through that, the inverse sine of V2 over V1. So that would be, we have things labeled, 20 divided by 120. Let's make that a little bit easier to read since that's taking up more space than I was expecting. And then you multiply that times the sine of angle 1, and the sine of angle 1 was the sine of 45 degrees. So if you divide these, 20 divided by 120 gives us 1.6666, and if you multiply that times the sine of 45 degrees, what we get is 0.11, rounds to about 0.118. So this would be the inverse sine of 0.118. And then if you go ahead and get the inverse sine of 0.118, we calculate that out real quick. Second sine of that answer. And what we get is, it rounds to 6.8 degrees. So that is the angle that we're looking for. So when this comes in, it comes at 45 degrees, which is about halfway between these two lines. But when it diffracts, it slows down so much. I actually didn't draw that line close enough. It would actually be very, very close to the normal line. It's almost heading along the normal line. So that's the last thing I wanted to discuss is if you do go to the beach over the summers you've been, you may not have thought about it, but if you go back to your memory, you may have noticed that when the waves come in, if this is the edge of the beach and here come the waves in this direction, the waves almost always seem to be coming straight in. But out in the ocean, due to winds and other factors, the waves may be traveling in this direction or that direction. Yet when they get to the beach, they're almost always heading straight in, basically right along the normal line from the boundary layer of the beach. And if we want to discuss very quickly why that is, using what we've learned, if we've got deep and shallow water, here's my normal line. So if the waves come in this direction, they slow down as they go into shallow water. So what do? Instead of going straight, they bend towards the normal line, which is closer to being at a 90-degree angle to the beach. What happens if the waves come in from the other direction? If they come in from this direction, instead of going straight, again, they're going to slow down. So they're going to bend towards the normal line. So as it gets slower and things speed down, what you see is that the wave direction continues to bend more and more towards the normal line. They bend more towards coming straight in towards you as you're at the beach, which may probably something you never thought about before, but we always try to throw in a little bit of application about where have you actually seen this, even if you weren't even noticing it was happening. So please go ahead and work on your Canvas questions, and let's be prepared to have a Zoom meeting so we can have some discussions with anything that you need help on. Good luck, and I look forward to talking to you on Friday.